Hi, I hope you guys are doing well. So, in this playlist, we are going to start reproducing this paper. Actually, the paper title is a highly optimized and sensitive body shape, body shape, uh, body shape based SPR biosensor for different light detection. So, this paper published in Nanoscale Advances. Okay, so. This is the work, this is the shape of PCF-based sensor. So we can see the PDF version actually. Okay. So this is the paper actually. Okay. The journal is Nanoscale Advances. So it's the Q1 journal maybe. So let's check. So Nanoscale Advances. The Q1 journal actually. Okay. So you can search on Imago. So it's the journal checker. Okay. So go there. And Nanoscale Advances. Okay, you can see now is the publisher is Royal Society of Chemistry, RSC. Okay, and it's a Q1 journal. Okay, so you can check its field actually: engineering, material science, bioengineering, chemistry, optics, atomic and molecular physics. Okay, so all the field it's Q1 journal, but recently it's at bioengineering uh, Q2 journal, but most of the three cases it's sorry, other course is Q1 journal. So it's a very good paper because the Q1 journal. So we want to reproduce it. So this is the model. Okay, so uh, we want to reproduce all the things, and we reproduce the okay, electric field distribution, then surface meshing curve, and then we'll plot wavelength versus loss curve, and then wavelength versus analyte RI, amplitude sensitive, and figure of merits. And okay, this thing, okay, this is the normal electric field distribution and Maxwell upward electric surface stress tension. So the new thing here. Okay, and then optimization part. Okay, I'll discuss all the things. Okay, step by step in the playlist. And the most important thing for the playlist is, so nowadays PCF SPS sensor are um, getting actually saturated, so you have to introduce new things, new analysis to publish it in very good journals. So uh, you have to do new analysis. Actually, you have to add new analysis. So I will discuss it later. Actually, in this video. Okay, so step by step, I will discuss it. Okay, so don't worry about it. So. Uh, in this video, I will just discuss about how you can design this geometry. Okay. And another thing, I will provide you the DOI of this paper in the description box, or you can search the title actually. Okay. So I'll provide the DOI. It's open access journal, so you can easily get the PDF version of this paper. Actually, it's free for everyone. Okay, it's not subscription based paper actually. So what they done in this paper actually, at first we can understand the result actually. So uh, first of all, the main problem of initial researcher who just entered the field, they didn't understand the things, how actually PC based sensors are actually working. So for them, um, and to just clear it how actually it's working actually. Okay, so basically this is the fiber part. Okay, so the silica, and with the air hole. This is the fiber part. So if you choose the circle, if you don't use gold and other channels, then this is the fiber part. Okay, so uh, of optical fiber, what actually the purpose of optical fiber? Optical fiber actually used in communication. So they pass through, they work on for light actually. So they pass data, light is spread. So because mm, okay, and okay, so in optical fiber, we pass light through the fiber. Okay, so uh, we have to design such a way that we can minimize the loss actually, right? So for SPS sensor, what we have to do, we have to design a fiber, and light will pass through some portion of the fiber. So that will be the core, and we have to confine the light at the inside the core actually, uh, by designing by placing air hole in such a way that you can confine light in a place actually. Okay, so when you confine light, then light will propagate through the core. Okay, I can explain from here. Okay, light will propagate through the core. Okay, so but we are using actually gold as a plasmonic material. So, uh, so when we will use gold as a gold or any other plasmonic material like copper, silver, or any other things, so then what will happen? Uh, Light will propagate, but we have to design it as such a way that from the core, some percentages of light will propagate through the plasmonic material. Okay, so then the light will interact with plasmonic material, and it will excite the electron at the resonance wavelength. So uh, then with the resonance wavelength or excitation of electron, we will detect the light that is available in the outside of the plasmonic material. So okay, so how actually it's working actually? Okay, so we are placing analyte. Analyte means for example blood samples actually. So um, so let's say it's analyte is blood. So we are placing blood outside the fiber. Okay. So the blood is available on the top of the um, plasmonic material light, right? So let me zoom it. Okay. So the blood is available on the top of the plasmonic material here. So when light will propagate through the plasmonic material, light will interact with the plasmonic material, and the Hmm. And light will decide which wavelength of light will be the resonance wavelength. So light will try to excite the electron of uh, free electron of the plasmonic material, uh, and the light of outside of the gold will decide which electron will excite it. Sorry, which light will excite the electron actually. So if you know the band gap actually and other things, so we know that we have to provide a minimum amount of energy to light. So let me just open it. Um, Let me download it. Okay. So, so then I can. Okay. So there you go. What it's talking about? Okay. Okay. So we know the band gap, right? So suppose for a electron, the electron require 2 electron volt energy to get excited, but you are providing, for example, 1.5 electron volt energy, so the electron will not excite it, right? So that's why you have to provide at least 2 electron volt energy. Okay, so that's the thing here. Okay, so so how we can calculate the energy from wavelength? For example, the light wavelength is 550 nanometer. Okay, so if the light wavelength is 550 nanometer, uh, then its energy is energy is equal to, we know the equation actually. Energy is equal to SF, right? Or is new, whatever you can say, SF or is new, whatever you can say, is equal to actually is. Okay, so it's the frequency actually, both are the frequency. So if we relate it with wavelength, then you can write it is equal to, sorry, is equal to hc by lambda, right? So lambda is here, lambda is wavelength. Okay, so c is the velocity of light, s is the Planck constant, lambda is the wavelength. So this is the wavelength. So the analyte will decide which the analyte of the outside of the plasmonic material will decide which wavelength of light will excite the electron to make surface plasmon. Okay, so that's the thing how it's work actually. So in the time of design, what we have to mm, take in our mind. So uh, we have to take in, okay, whatever. We have to design the sensor such a way that we can confine light anywhere of the fiber, and from there light should propagate through the plasmonic material. That's why light can interact with the plasmonic material, and then it can create resonance, and that's how it can actually sense the outer analyte actually. Okay, so here you can see the result. If you can see the results, you will uh, understand better actually. So here you can see that, for example, these two graphs looks good. Okay, so here you can see that the for this curve, it's so okay, its RI is refractive index is 1.42. Okay, its refractive index is 1.42. So for that, okay, resonance wavelength kind of 940. We don't know actual the resonance wavelength, but let's say it's 940 nanometer. Okay, but for the light 1.43, the resonance wavelength is kind of let's say 1200 of whatever. Let's say 1200 nanometer. So when we are placing analyte of refractive index 1.4, forget it, 1.42, then the electron of gold will excited at uh, 940, and when we are placing analyte of 1.43 refractive index, then electron will excited at 1200 nanometer light. Okay, so that's the thing. So then this 1200 the wavelength of 1200 nanometer will absorb by the gold, and what will happen actually? So let's say this is the fiber. Okay, okay, let me write clearly. Okay, let's say this is the fiber. Okay, so this is the fiber. We place gold around the fiber actually. So we place gold around the fiber, and that is something air hole. Okay, whatever. So light is propagate. We are okay. We are injecting light from the inlet of the fiber, and we are collecting light from the outlet of the fiber. Okay, so uh, we'll place the detector of wavelength actually. So we are uh, okay. I'm sorry. So we are inserting light from the inlet of the fiber, and what will happen at the resonance wavelength, for example, resonance wavelength is 914 nanometer, then this wavelength will be absorbed by the gold, and we will not get the light of 914 nanometer from the outlet. So then we will detect that okay, 914 nanometer wavelength of light is not available at the outlet. That's why we can say that then light is the refractive index of final light is 1.42, right? So if we found that the if we cannot find the wavelength of for example 1200 nanometer, then we can decide that it's 1.43 of refractive index, right? So that's how it's work actually. Okay, and uh, you may ask for that okay, so you are talking about refractive index, but what's about biological sample, right? For example, um, different cancerous cancerous cell or something like that. So for that case uh, what's happened actually, for example, a blood sample that has no cancer cells, then its refractive index, for example, 1.3 4 1.341, for example, 1.341 refractive index of a blood sample. That is very normal for normal blood sample. Okay, then it affected with, for example, Mm, malaria, for example, malaria. So then your blood sample affected with malaria, then its refractive index will not be 1.341. Its refracting index then, for example, let's say 1.41, 412, whatever you can say. I don't know actually the exact value, but let's say 1.412. So then normal cells refractive index is 1.341, and the cancerous malaria affected cells refractive index is 1.421. So then you'll find that the resonance wavelength for 1.341 will kind of, for example, like this at for example, let's say 510 nanometer. Okay, let's say. But for 1.421, the resonance wavelength is, for example, at a 1300, okay, nanometer. So it's you can clearly differentiate between two cells, right? So then you will decide that okay, so it's normally a normal cell or it's the uh, malaria affected cell. That's how it actually work. Okay, so I think you understand the basic things of PCF-based sensor for biosensor or any other sensor. Okay, another thing is someone actually working on temperature sensor or some other things. So if you want to learn about how PCB temperature sensor actually work, you can comment me. I'll discuss in another video how actually temperature based space sensor actually work. So um, okay, okay. So as I told you that today's video I'll discuss about mm, I'll build this geometry of this model actually. Okay, so let's go to the COMSOL file. Okay, maybe okay, no worries. Um, okay, so I'm sorry, not today. We'll discuss about the geometry of this model at our next video. So for today, for today is the end of this video. Okay, thank you.